Hi students, today we are going to discuss inverse of a function. Before discussing inverse of a function, I hope you have went through my session on a composite of a function. That if I have two functions f and g, f is a function from the set a to b and g is a function from b to c, then how the composition of the function f naught z, okay, which is mapping from a to c. Just a very quick recap. Suppose I have a function f, okay, from a to b. Okay, this is the set A, this is the set B. I have a function f which maps an element x in the set A to the element y in the set B, and I have another function from B to C, and that function I define g as B to C is that, and if I get an element y in B, it maps by means of the function g to an element z in the set C. Now what I can do is that I can have a function from a to c, okay, so that we known as g naught f. Okay, so what it does, it maps to the element x in the set A to the element z in the set C. So that is called composite of the function, composition of functions. In case someone has not went through this very properly, please look into my previous class on composition of functions. Now, before going to discuss about inverse of a function, I would like to tell you very important thing is that if f and g both are bijective function, then g naught f is bijective. And if g naught f is a bijective function, then f and g can be bijective, but that is not mandatory. That is not must. Okay. So I repeat, if g naught f is bijective, then f and g both can be bijective, but it is not a very strict rule. The strict rule is that if g naught f is bijective, then f has to be injective and g has to be surjective. I repeat, if g naught f is bijective, then f has to be injective and g has to be surjective, must. Okay, so that is the thing. Now let us come back to our discussion on inverse of the function. Suppose I have a function f from the set A to B. Now, the inverse of this function, if possible to exist, we will discuss under what condition the inverse of a function exists. But if it is exist, it should be another function g which maps from B to A. I repeat, if I have a function f defined on the set A and B, f colon A to B is a function defined, then its inverse, if its inverse exists, and if the inverse is g, g should be a function from the set B to A. Now what is the condition? The condition are that g can be a inverse of the function f if and only if G naught F is equal to IA. That is the identity function on the set A. Okay, let us understand. Okay, there is another condition. It is F naught G should be equal to IB. Right? That is the identity function on the set B. Let's understand. So, by means of pictorial diagram. So, this is the set A, this is the set B, and there is a function from A to B, that is the function F. So, this is the function F, which maps an element, for example, X to Y. Alright? Now, I have another function G here, which maps from the element B to A, right? So suppose this is Z in the element, so this is G, right? Now what is the composition of the function G naught F? G naught F is this one. This is G naught F, right? So now what will be G naught Fx? G naught F of X is actually Z here, right? Correct? So Z equal to Z naught Fx. This implies Z equal to Z of Fx. G of Fx is nothing but Y. So Z equal to Zy. Now, the point is that if G naught F is an identity mapping or identity function on the set A, then what will happen? This Z will become X. Right? So that means as if this will turn out to be X, not Z. Or we can say Z is equal to X. Then you can say that yes, this is the first condition has to be satisfied, that in order to that G becomes the function G becomes the inverse of the function F. And similarly, F naught G has to be IB. What is F naught G? Let us do this thing. So suppose this is the set B, this is the set A. So I have a mapping G which maps an element X in the set B to an element Y in the set A. I have another function, suppose this is a set B again, and which maps an element Y to the element Z in the set B by means of F, by means of the function F. Then what will be F naught G? F naught G will be this function. This is F naught G. Correct? Fine? F naught G. So now, what F naught G will have? F naught G will map the element X in the set B to the element Z in the set B by means of this one. So what is G naught Fx? F naught Zx. F naught Zx is actually Z. Z is equal to F naught Gx. Now, if this becomes Z become X, okay? If Z become X, then what will happen? It will become an identity function on the set B. That means what will happen? X equal to F naught Gx. So that means that F naught G is an identity function on the set B. So these are the conditions has to be satisfied if G becomes a inverse of the function F. Generally it is denoted as F inverse. G is equal to F of inverse. Clear? There are two preconditions. Okay, as I said, G naught F has to be IA, F naught G has to be IB. Now, if inverse function exists, it has to be unique. It is unique. What does it mean? I have a function f whose inverse is f inverse. I cannot find any other function which is the inverse to the, apart from f inverse, is the inverse to the function f. That means literally what I can say is that if I have a function f whose inverse exists, then it is not possible to find two other functions g and h where both g and h are inverse of the function f. It is not possible. I'm sorry. Sorry. I'm sorry. So it is not possible that two different functions is inverse to a function, right? It's not possible. So final conclusion is that if inverse of a function exists, it is unique. Second one is that a function to become an invertible function, it has to be, the function has to be a bijective function. What is that? For example, I have two functions. I have a function f. Its inverse exists if these conditions actually getting satisfied. And if I club together, I get another thing is that the function f has to be bijective. Okay? So a function f is invertible if it is a bijective function. Clear? Right. So let me write two things what we have learned. Inverse of a function if exists is unique. And number two, a function is invertible if it is bijective. That means both injective and surjective. So what we see is that inverse of a function exists, a function if exists is unique, and if function is invertible, that means its inverse is possible if it is a bijective function. Alright. Now we are going to see how to find the inverse of a function by means of an example. Okay? There are a few steps involved. So suppose I have a function fx. F is a function from the set of real number to the set of real number, and it is defined as fx equal to square root of x plus 4 minus 3. Now we need to find the inverse of this function. How to find? That we are going to see. There are few steps involved, very simple steps. Let's have a look into it. The thing is that first step, what we will do, we will replace fx by y from here. We will replace fx by y and we will write whatever is written here, x plus 4 minus 3. Second step, that is our step number 1. Step number 2 is that replace all the occurrences of x in the right hand side by y and the single occurrence of y in the left hand side by x. What does it mean? So it means is that whatever the occurrences of x has happened in the right hand side, I will replace it by y. So it becomes y plus 4 minus 3, and the single occurrence of single occurrence of y in the left hand side I am going to replace by x. Now what is the next step? Is that solve the equation for y. Very simple. So third step is that I will make what? X plus 3 is equal to square root of y plus 4. This implies y plus 4 is equal to x plus 3 whole square. This implies y equal to x plus 3 whole square minus 4. You can further simplify it. So that implies, and okay, let's simplify. This implies y equal to x square plus 6x plus 5. Now final step is that replace y by f inverse x. So the final stage is that I will write, instead of y I will write f inverse x, and whatever is there in the right hand side, let's keep it intact. So I get the inverse of the function f by these 4 steps. Okay? Fine. What I will suggest you, have a look into it in another 2 minutes, that how I discuss about the inverse of a function, under what condition inverse of a function exists, and how to find the inverse of a function. Alright. Our next topic, we are going to discuss about that binary operation. Binary operation is a kind of an operation where I need 2 operands and 1 operator, right? Let's see, I have 2 elements A and B from a set A. There are many elements. Let's take AB, 2 arbitrary elements in the set A, and I define the operation star on the set A. Now the condition that if A star B is again belongs to A, then we can say that operator star is a binary operator, right? So that means what I am doing, I am taking 2 elements, any 2 elements in the set A, and I am making an operation on those 2 elements, and I will get some resultant value. Now that resultant value, if it belongs to the same set A, then you can say that yes, this operator star is a binary operator, and the entire thing is called binary operation. Why it is binary? Because I have 2 operators. The operators are A and B. That is called, there are there are 2 operands A and B, and there is 1 operator star, right? So there are similarly you will be able to see that unary operation, that is a different topic we will discuss later. Now there are some specific properties of a binary operator. So let's discuss about this in details. Sorry. Let S be a non-intercept and star be a binary operator defined on S. You know, this English statement can be reduced to a simple mathematical expression. What is that? That means for any two arbitrary elements A and B belongs to S, A star B must be belongs to S. So whatever I have discussed in English statement like this is actually meaning as this. For all AB belongs to S, A star B belongs to S. Then you can say this is a binary operation. Now, it has some properties. Okay? It has some properties in the sense is that we will discuss about few properties. If these properties is satisfied, then you can tell, okay, that operation is actually satisfies this kind of properties. What is this? Number one is called associative. Associative property. What is that? Now, for all A, B, C belongs to S, A star B star C should be equal to A star B star C. That means for any three elements, for all elements A, B, C, if I take first the operation on B and C, the resultant value, if I make a operation with A, whatever the final result value I am getting, that should be equal to, if I make A and B first, get the resultant value, and that resultant value if I do with C, and get the same value. For example, in our normal operation like plus, minus, okay, these are satisfied by the associative property. Second one is called commutative property. What is that? Commutative property. Now for all AB belongs to S, A star B should be equal to B star A. Correct? For example, plus, minus, okay, the normal plus minus we are aware of are actually satisfied by the commutative property. But if you see the Cartesian product on sets, it is not commutative, right? A cross B is not equal to B cross A. Correct? Now, third one is that identity element. Okay, the identity element on a set with respect to a operation, binary operation, exists if it satisfies this condition. Is that it's called identity property. identity property. What is that? For all A belongs to S, there exists an element E belongs to S such that A star E is equal to E star A is equal to A. I repeat. For all A belongs to S, you take any elements, for all the elements in the set S, if you get an element E belongs to the same set S such that A star E is equal to E star A equal to A, then you can say that the set S with respect to the operation star satisfying the identity property, and that E, the element E, is known as the identity element. Okay, so this E is known as identity element. Clear? Next one is that inverse property. Here is that for each element A belongs to S, there exists an element B belongs to S such that A star B is equal to B star A is equal to E, the identity element. Then you can say that yes, inverse property is going to be true. Let me write and we will discuss further. So what you can say is that for each A belongs to S, there exists an element B belongs to S such that A star B is equal to B star A is equal to E. This E is the identity element what we observed in the earlier property. Then we can tell that B is known as the inverse of A. This B is known as inverse of the element A. Sorry. Two important things I would like to say here. When we looked into the identity property, we see for all A belongs to S, for all A belongs to S, there exists an element E belongs to S such that this. That means for all the elements in the set S, the identity element is only one. But in case of inverse, for each A belongs to S, there is a difference to be noted here. Here I wrote for all A belongs to S. Here I wrote for each A belongs to S. That means for each and every element A belongs to S, I get another element B belongs to S such that A star B is equal to B star A equal to E. Then you can say that B is the inverse of A. So what does it mean? It means that identity element on a set with respect to a binary operation is unique, is only one. But inverse of each element in the set S with respect to the binary operation is actually each and every element has its own inverse. But inverse, if exists, is unique. That means the inverse of the element A, if it is A inverse, it is unique. It is not possible to have any other element to inverse of A apart from A inverse. Okay, let's take it some other way. Suppose I have element A in the set S with respect to the binary operations star defined on it, I got two elements B and C. Shall that A star be equal to E, the identity element, and A star C is equal to E? It's not possible. If it is, then we can say that okay, no, the inverse of the element A doesn't exist.